In the last module, we covered the controls over soil formation. Here, we'll discuss the controls over soil loss. Now, the authors state that soil formation depends on the balance between deposition, erosion, and soil development. That is, the changes that soils undergo in place. So again, when we're thinking about soil formation, we're thinking about deposition, erosion, and soil development. So the same factors that we think about for soil formation can also be important for soil loss. So within a hill slope complex, for example, areas of deposition are underneath areas of erosion. So soil formation, in part, is dependent on soil loss from another area. Now, in general, when we're talking about soil loss, we're going to be talking about erosion. And erosion removes the products of weathering and biological activity. It's especially pronounced in young soils. So when we go to areas of relatively young soils, these are areas where you'll have a lot of erosion that occurs. But it's also important in old soils and in places that have been in place for a long time. There's still erosion that occurs, and as long as the processes that are generating soils are balanced by the processes that remove products of soils, erosion is also important for old soils. And just as with new soils, erosion is going to be taking away material, that still occurs in old soils too. Now, as far as the different factors that determine erosional processes, a lot of these are associated with state factors, and topography is one of those, but also the properties of the surface materials and the pathways by which water leaves the landscape. So when we're thinking about erosion, we're going to think about topography, we'll think about catinas, for example, but also what those properties are of the surface materials, and we'll discuss that in just a second, as well as the pathways by which water leaves the landscape. If water doesn't leave the landscape, you're not going to have erosion to the same degree that you do when water leaves the landscape relatively quickly. Now, the first example of erosion is something called mass wasting. And this is an example of mass wasting. It's essentially landslides. So here you have an area where you've had a large movement of soil downhill from up here and deposition at the bottom. Here's another example where you can see you have an exposed rock and that you've had multiple events that have occurred, some on top of the others, which are movement of these materials in large catastrophic events. Mass wasting is defined as the downslope movement of soil or rock material under the influence of gravity, but without the direct aid of other media such as water, air, or ice. So this is movement of material, but not because there's water moving, it's not because wind is blowing it or ice is scouring it. It's just gravity all by itself. Now, mass wasting is also dependent on fine scale processes, but in general they're massive events. And when we take a look at whether you're going to get mass wasting or not, movement of soils, landslides, we're going to think about the shear stress. And shear stress is the force parallel to the slope, and it's the balance between gravitational force and friction. So here you can see that you have a relatively moderate slope, and the force parallel to the slope is the shear stress, and that goes right here. And then in addition, you have gravitational force and you have friction. Gravity is going to go and straight down. You'll have a friction force, and the balance of these is going to determine whether you exceed the shear stress or not. Shear strength is the shear stress that a soil can sustain without slope failure. So although, for example, here you're more likely to have mass wasting occur, movement of the soils downslope, whether you do or not depends on the shear strength of the soils. Now, what generates shear strength? Well, it's essentially the internal friction among the individual components within the soil. So one of those factors is the cohesion among the soil particles and water molecules. And to a certain degree, the more water that you have, water is going to enhance the internal friction, and that's going to resist mass wasting. And anytime you go to the beach, for example, and you build a sandcastle, you tend to do that with relatively moist soil instead of very dry soil. And a small amount of water really enhances the cohesion of soil particles. In contrast, if your sand gets too wet, for example, you're not going to be able to build with it, and high water content reduces the frictional strength. So if this is water content on the x-axis, and the strength is going to be here on the y, there's a certain midpoint where your shear strength is going to be highest. Too dry, too wet, and you're more likely to have mass wasting. In general, fine particle soils have lower slope thresholds of instability than coarse textured soils. And what that means essentially is that if you have really clayey soil, that you can build bigger hills with it than you can sand, which is going to tend to collapse. In addition, roots also increase the resistance of soil to downslope movement. So in a situation where you have your slope and you have soils on top of it, if you have a lot of roots that are in there, that's going to resist the movement downhill a lot more so than if you didn't have those roots. Now, water movement is another factor that's going to move soils around and cause erosion. Here's an example along the Arctic coast where you can see collapse of the soils and movement, and that's essentially waves coming up against the shore and pounding up against here and moving those soils. And that's one of the erosive effects of water. In addition, this is a photograph from Mount St. Helens not long after the 1980 eruption, and you can see this is all new material that had been deposited, but water moving through that system had scoured it out and made deep channels. It had only taken a few years to generate a valley that was relatively deep. There are other examples on different scales on the landscape of moving of materials due to water, and you can really see them here. In addition to water moving soils, that wind can also play an important component of moving particles around. And you can see here an area that had been scoured. Soil level used to be right here, and wind had gone through and scoured it out, and all you have left are the roots that are remaining beneath each of these plants. This here is a photograph of the Great Sand Dunes National Park in southern Colorado. In the background you have the Sangre de Cristo Mountains, and the Great Sand Dunes are on the order of 300 feet high. So really tall. And in general, what you have in this valley, in the San Luis Valley, are winds that blow this direction, and they pick up material and deposit them against the base of the Sangre de Cristos, and you get these huge sand dunes, some of the tallest sand dunes on Earth in this area right here. And so wind is going to be moving material around in this valley system from one end of the valley to the other. Now, sometimes the movement of those particles is not that apparent. Other times it's very apparent. This here is a dust storm approaching Stratford, Texas. Photo date on this is April 18th, 1935. And you can see a giant cloud of dust and soil particles basically about to cover the town. And this is during the Great Dust Bowl. Here's a picture that was taken just four days earlier on April 14th, 1935 in Spearman, Texas. And again, these huge, massive clouds of dust and soil material coming in. Now, we tend to think of these giant dust storms, at least in North America, as being a product of cultivation, bad cultivation practices, and being a relatively rare phenomenon. But in drier areas, we can still see those same general patterns. So this is a dust storm that's approaching Phoenix, and this right here is where the local baseball team plays, the Arizona Diamondbacks. And essentially the term that's used for this in the United States is a dust storm, but internationally it's referred to as a haboob, which is an Arabic word for dust storm. And essentially what you have is that you can see that there's a thunderstorm that's approaching this area right here. And in general, what happens when a thunderstorm is approaching, that you have winds that are moving in to the center of the thunderstorm. But once those rains start to fall, you have a reversal of the winds, and they start to come out from the center. And as they do that, they're going to pick up a lot of material, and there's a front system right in front of all the rain that's going to move those materials. So during the thunderstorm formation, the winds move in a direction opposite to the storm travel, and that's going to be that inward movement initially. And then when that storm collapses and releases precipitation, those wind directions reverse and they gust outwards. And that downdraft, or that downburst, can have very, very high winds, and those winds are high enough to pick up all the loose particles on the soil surface and move them in a wall. And so this happens a couple times a year in places like Phoenix, but it happens throughout the world in dry areas. And that's just an area where, in arid systems, where you have a lot of movement of soil material, not through water, but by wind. And so what we saw about to envelop Phoenix is really not that different in many respects to the Dust Bowl era and what you saw in the 1930s. The only difference is that this was caused, at least in part, by bad cultivation practices, whereas the other is more of a natural phenomenon and not necessarily directly associated with human activities.